Quantum two-set on low-dimensional systems is QMA1-complete, direct embeddings in black box simulation. Joint work with Sevak Garibian and Daniel Nagai. Let me start by introducing the quantum satisfiability problem, or quantum K-SAT. The input is a k-local Hamiltonian HI, where all the HI are projectors. Each HI is k-local, which means it acts non-trivially on at most k qubits. We need to distinguish between the yes case, where lambda min of h is 0, and the no case, where lambda min of h is at least 1 over poly n. In contrast, we also have here the more well-known k-local Hamiltonian problem, where we don't have the restriction that the HI are projectors, and we also have additional inputs beta and alpha. And in the yes case, the only requirement is that lambda min of h is at most alpha. So we conclude that KQSAT has a stronger promise in the yes case. The Hamiltonian must then be frustration-free, which means that all the local terms have a common ground state, and this ground state energy must be 0. The corresponding complexity classes are QMA1, where there exists some verifier that on input x exists some state psi, such that Vx accepts psi with probability 1. So this means it has perfect completeness. For QMA, we only require acceptance probability 2/3. The no case of both classes is the same. There, all states psi are accepted by the verifier with a probability of at most 1/3. And the complexity of the problems is in P for 2QSAT, shown by Bravi, whereas the 2 local Hamiltonian problem is already QMA complete by Kempe, Kitaev, and Regev. And classically, we have also, of course, 2SAT in P, and max 2SAT is NP complete. And max SAT can be regarded as the classical version of the local Hamiltonian problem. 3QSAT is QMA1 complete by Gossett and Nagai, and 3SAT is NP complete, of course. And in this paper, we mostly study the quantum K by L SAT problem, where again we have some Hamiltonian H consisting of local terms HI, where here each HI is 2 local and it acts on a Q-kit and a Q-lit. So in total we get a bipartite interaction graph. 3x5 QSAT is QMA1 complete, shown by Ilda and Regev. 2x3 QSAT is at least known to be NP hard, and 2x3 SAT is NP complete. We also look at quantum SAT on a line of qubits. We know it is QMA1 complete for d equals 11, shown by Aharonov and others. And classically, 1D SAT is NP for any local dimension. We know also that on a line of qubits, which here we also call 3x3 line, there exists a frustration-free qubit construction with a unique entangled ground state by Bravi and others. So we don't know whether the line of qubits is hard, but at least we know that it can embed an entangled ground state. So, what is the smallest local dimension that can encode a QMA1 hard problem? Let's go over our answers here. First, we show that 2x5 QSAT and 3x4 QSAT are QMA1 complete with a soundness of 1 over n squared. That means that our reduction embeds an n-gate verifier V into a Hamiltonian H, such that the norm of H is O of n, and in the no case, the minimum eigenvalue is omega of 1 over n squared. Here we have a table summarizing all of our results. So the main results are 2x5 and 3x4. Then you get everything to the right and below for free. And these were the results of Elder and Regev. And these NP hardness results were from Nagai. And the P result from Bravi. We also show that the 3QSAT problem is QMA1 complete with a soundness of 1 over n squared. So this is an improvement of the same result from Gossett and Nagai, who only had 1 over n to the 6th power. We also show the first QMA1 hardness result for lines of alternating particles. So the setup is like this. So you have Q-trits, Q-dit, Q-trit, Q-dit, and each edge here represents a Hamiltonian that acts on the Q-trit and the Q-dit. We show that 1D 3x D Q set is QMA1-complete for D equals 76,176. The reason for this huge number is that we do a black box simulation of an arbitrary 1D D/D Q set on a 1D 3x D prime Q set, where D prime now is in O of D to the 4. So that's where the huge blow-up comes from. This is a black box simulation that preserves soundness in the no case, similar to the analog Hamiltonian simulation a la Bravi and Hastings, Qubit, Montanaro, Piddock. And our hardness result works by embedding the 1D 11x11 Q set of Nagai to get QMA1 hardness. So we also ask the question, how difficult is 1D 2x D Q set? We show that there exists a frustration-free 1D 2x4 Hamiltonian with a unique ground state that is entangled across all cuts. So we leave the question whether it is QMA1 hard still open. Now let's look at the 2D Hamiltonian construction, which is at the heart of our 2x5 completeness result. Let's revisit first Kitaev's circle to Hamiltonian embedding. The idea is that you build a Hamiltonian whose ground state is the history state, where history state has this form. So you have a superposition of these time steps. So each CT is a logical time step which encodes the time step t in tensor product with a substate psi to which the gates U1 to UT have been applied. We have all time steps of applying a circuit gate by gate in superposition. Here we have some Hamiltonian H clock whose null space is spanned by these time steps. And in the following, let's just consider our projectors restricted to this clock space, which is the span of this C0 to CT. And the main gadget is sort of this transition Hamiltonian, which implements the unitary U from time step t to t+1. So these terms work like this. So if you have CT to t+1, you want to apply U. From t+1 to t, you want to apply U dagger. And then we have these additional terms to make the whole thing a projector. And yeah, so what Gossett and Nagai shows, that if you have these selection projectors, which look like this, and also these gate projectors for one local gates, then you can embed a circuit into a Hamiltonian. And their main tool is this 2D clock, which you can get by placing the H clock Hamiltonian on the X register and also on the Y register. So what we still need to show in this work is that there exists a 2x5 local H clock and also 2x5 local HT 2t+1 of U, and also one local selection projectors and identity gates. The main basic building blocks of Gossett and Nagai are these here. So we can look at our clock states as these dots in a grid. And then we can look at what can we do with these two local gadgets. So for example, because these individual projectors are one local, we can build sort of a projector that selects a quadrant. We can build a unitary transition on the y-axis. So here these arrows indicate that these transitions would sort of continue along the x-axis in the full row, which is just because we want two local gadgets and the H23 takes up one locality and the U takes up the other. And so yeah, so if we want to restrict the locality of these transitions, then we can apply in tensor product this C greater or equal 3 projector, but then we only have enough locality to implement an identity transition. But then these would only continue to the right. Additionally, we can build a conditional transition indicated by a dashed edge, which then also goes in both directions. This dashed edge would only apply if there's a 1 in the control qubit. Now, one can combine these gadgets to a CNOT gadget. The basic idea for the CNOT gadget is as follows. So you have some input state here, some output state here, and if you have a 0 in the control, you first apply UX, then UY. If you have a 1 in the control, first UY, and then UX. Effectively, the gadget applies this unitary from top left to bottom right. For suitable non-commuting UX and UI, you can realize a C0 gate up to 1 local unitaries. But so it's not as simple as this looks because of the spatial restrictions of the gadgets. So for example, if we want to apply a UX on these two time steps, we really can only apply it along the whole column. And so that's why you would get these additional edges. And then you have this little square here, which sort of is a contradiction, because from here to here, it would say that UX and UI are the same as UI and UX, which is really what we don't want, because we need non-commuting UX, UI. So we need a more complicated gadget, which is this. And this is our version of the gadget, which is very similar to GN13, but we had to perform some modifications to apply our own proof techniques to get the improved soundness analysis. And so the basic idea how this works, and I won't really go into detail, is that if you have a 0 in the control qubit, then all these dashed edges here, the horizontal edges become solid, the vertical edges are removed, and then you get the path from here to here, first x, then y, and for the 1, it's similar, first y, then x. And we have some time steps here which are penalized because you have this contradiction square again, and then that just means that ground state or the null state will not be on any of these time steps. We show correctness via unitary labeled graphs. And so note that the analysis of GN13 was just numeric, so it's a slight improvement here. Now that we have our gadgets, we can assemble them to a full circuit Hamiltonian. So here, this is also our gadget for the 1 local gate, super simple. This is our C0 gadget from the previous slide, and this is again a 1 local gate. And so we place them in a diagonal, and we add these zigzag edges, which is just sort of to highlight these additional edges connecting the gadgets. And each of these is just an identity transition, so just like a black edge. And so what we can now use is the null space connection lemma, which I show on the next slide. And this one will give us correctness and also the spectral gap. The idea is that we have some circuit Hamiltonian on a graph of clock states. So yeah, we have our graph here. And it consists of these little gadgets. Each box is a gadget with an input node and output node. So here we have input, output, input, output, input, output. And the gadgets are connected with these zigzags. H1 consists of the gate gadgets, which is there's T circuit Hamiltonians on clock states. So we have sort of a small circuit Hamiltonian here. And these clock states are disjoint between the gadgets. So here we have the example of Kitaev's Hamiltonian. We just added some identities to make this, to have this gadget layout here. And what we have is that the null space of each gadget, which should be this, is spanned by sort of a local history state. It's just on the time steps t-1 and t. And yeah, so the zigzag edges are just identity transitions from Vi to Ui plus 1, and these are in H2. And yeah, well, then the main statement of this null space connection lemma is that if H1 and H2 have this form, then the total Hamiltonian embeds the circuit U1 to UT from input node U1 to output node VT. And the total Hamiltonian has a spectral gap H. And recall that gamma of H is the smallest non-zero eigenvalue. And this is a spectral gap of H1 over T squared, which is the number of gates. In our case, this is just a constant because these gadgets are constant. And yeah, so this is actually a quite useful tool, this null space connection lemma. I was able to use it in a newer paper of mine towards the universal gates for QMA1. And one theorem in that paper is that the gapped clique homology problem, as defined by King and Kohler, is QMA1-complete. The challenge there was that the gadgets of KK24 only work for 4-qubit integer projectors. And although they do provide more general gadgets, only correctness proofs for the 4-qubit gadgets are provided. But then I also, for the containment in QMA1, I need the Toffoli and Hadamard gates. And I have some gadgets to implement these. I won't go into detail here, but the takeaway is that with the null space connection lemma, we only need to prove local properties of the gadgets. And because these gadgets are finite objects, we can just analyze the Hamiltonian in a program like Sage and compute the null space exactly. Now let's go back to the 2x5 clock. And so the challenge here is how can we use qubits to any useful degree when we only have 2 local projectors. And recall that we need a 2x5 clock with 1 local transitions, ht to ht plus 1, and selection projectors c less than or equal t or c greater or equal t. And so the very basic idea is to use logical qubits as with indicator qubits. So for example, we can implement a logical qubit on a q6-it and 3 qubits. So for example, we have a logical 1, which is the superposition of these two states. We have a 1 here, and then only zeros. And on the 4, we get 1, 0, 0. So we have an indicator. So we could do now a projector that just selects the 1 head with a 1 local qubit projector. And this structure here can be enforced with 2x6 projectors. But still, to use a Q6-it to implement a logical qubit is not good enough. So we need a more clever approach. And the idea then is to start with a 3x4 clock and from that build a 2x5 clock. Recall that Elder and Regev show QMA1 completeness of 3x5 QSAT. The basic idea there is that each 5-dit is regarded as these 5 phases: unborn, alive 1, alive 2, alive 3, and dead. And essentially sort of the gates are only applied on these alive states. But then what we observe is that essentially 2 alive states already suffice in conjunction with the 2D Hamiltonian, and so we get that 3x4 QSAT is QMA1 complete. So then what remains is to transform this 3x4 clock to a 2x5 clock. The basic idea then is to embed the logical qubit on a Q5-it with these labels and 2 qubits. So on the logical Q5-it, we can really only use 2 indicator qubits, so we have to combine the indicator qubits for U and A. And for the logical 4-it, we really only have 1 indicator qubit left. And so with these indicator qubits shaved off to reduce the dimension to 5, there's not that much we can do, but what we can still do is we can identify with a 1 local qubit projector the U, the D, and these qubits, and we can also identify U or A just by a projector onto the 1 on this qubit here. And we can even transition between U and A by flipping this qubit. And now we can combine these logical states to the clock states, where each clock state is a superposition of these 4 sort of logical standard basis states. And in these 4 states, we basically just evolve the DA2 to a DA1. And then these states are set up such that from A1 to A2, you can form 1 local transition on a 5-it, so that we get this 1 local transition between a Ci time step and Ci plus 1 time step. So finally, let's go to the 3x-D clock, 3x-D SAT. So recall that we want to do a black box simulation. So we have some Hamiltonian on Q-dits. We want to transform it to some Hamiltonian H prime on QD prime-its and Q-trits. And the basic idea is that sort of this Q-dit gets embedded into this range here. So we sort of split these in half, and then the Q-dit is embedded on this whole D prime by 3 by D prime space. And what we show is that then there exists some local isometry such that h prime is equal to h up to this isometry. More formally, we show this theorem here. So we're given a Hamiltonian on a line of n qubits, and each term is PSD. And we show that we can efficiently compute some h prime on the 3 by d prime line, such that lambda min of h is equal to 0 if and only if lambda min of h prime is equal to 0. And the spectral gap is also preserved up to a factor of the norm of h. And so this is how the Hamiltonian will look like. The idea is to logically split the QD primates into two QD prime primates. And then each d prime prime by 3 by d prime prime system logically represents a QDIT. And then we implement some Hamiltonian, h ball, to move the logical QDIT between the QD prime primates. So sort of the information in a superposition gets shifted between these outside d prime primates. And then this allows us to simulate the original hi plus 1 locally on QD primates. So because at some point the information is here and here, we can then, up to some local isometry again, apply the original Hamiltonian h12. And so let me sketch how this thing works. So the idea is we have some h ball, which logically works in sort of a balls and bins type game. And so the bins contain red and black balls, and each QD prime primate is the bin of capacity 2D balls. A QTRIT has a capacity of 1 ball. A logical state I had is then represented by some red balls and some black balls. And the Hamiltonian h ball just enforces a superposition over all placement of these balls. So the logical state is then sort of the superposition of all configurations. And so we have this extra ball here just to avoid that there would be a configuration where two adjacent bins are empty. Which is sort of like a technical aspect of the Hamiltonian construction. And what we can then do is read or update the logical I from the encoded in this state I had by only acting on the configuration where the bin is full, so like this, and it has an even number of red balls. So we wouldn't act on this configuration. This is sort of only a transitionary configuration. And so the example for the 2D head, for the 2 head on a Q bit would look like this. So we have this state, and then these balls can just move around. And the logical state is a superposition of all these configurations. Now let me conclude, finally, with some open questions. So first, what is the complexity of 2 by 3 QSAT? Also, 2 by 4 SAT or 3 by 3 SAT? What is the hardness of 1D QSAT on QDITs with D less than 11? Here, the issue of our black box approach leads to a huge second dimension. And another question, is 1D 2 by D QSAT still QMA1 hard? Is 1D 2 by 3 QSAT instances with do there exist 1D 2 by 3 QSAT instances with a fully entangled ground space? Thanks.